Hello everyone, welcome to this video. In this video, we want to build a circuit, RL circuit and RC circuit, and to show you the different types of power, the active power or average power, the reactive power, the instantaneous power, apparent power, how to calculate the power factor in such AC, RL or RC circuits. Okay, so we need to open MATLAB. So once you open MATLAB, you will see this screen. You go to Simulink here, click Simulink, and then we need to create a model, blank model. So we click Create Blank Model. So now we have here the window of our model, and we will start build the circuit. And once we are building an AC circuit, so we need to have an AC voltage source. So you can go to the library, you can look for Simscape, then electrical, then specialized power systems, then you scroll down until sources, click on sources, then you will have all types that are included in MATLAB as types of sources. So I want to have AC voltage source, so I will drag it to my model, and then I have this AC voltage source. So you can drag it and put it wherever you want in this model. Okay. And then I need to have a resistor. So I go to the library once again. I go to specialized power systems and the passives. And from the passives, I will select series RLC branch. I select one for the resistor. I select another one for the inductor or the capacitor in my circuit. I need also to have a current measurement source. You can double click anywhere in the model, you type measurement. So here are the measurement devices. So I want to select one current measurement device. Again, I'm double click, I'm selecting the voltage measurement device here, and double click, I'm typing again measurement, and I'm selecting the power measurement device. So these are the devices that I need to measure different values. So let's start building the circuit. So I need to connect the current source in series with the circuit, since the resistance and the reactive element will be connected in series. So these are connected in series. So as you see here, we have our elements. I will start with this element and select the branch type to be only resistance. So, and to have its value to be 3 ohms. So I will do apply and then okay. I can also rename it. So I will remember that this resistance is equal to 3 ohms. Okay, so the other element, I will start with the inductive circuit. So I will double click on it. I will select L, which is the inductance. And for the inductance, I want to have 1 to the power of -2. So it will be 100 Henry. So apply, okay, and I can write it here. So I will not forget it. I will say L is equal to 0.0, sorry, L is equal to 0.01 Henry. So this is the value of the inductor that I selected in this circuit. And then you can close the circuit. So the circuit now is closed. And we can now connect the different measuring devices. So let's check the parameters for the source. For the source, we need to have the peak amplitude equal to 10 volts, the phase angle equal to 0, the frequency equal to 50. So here are the parameters for the source, and now I will do okay. So now I want to have an Rms block in order to measure the variables of the circuit. So I'm typing RMS anywhere in the model, and this is my RMS block. So let's have it for the current first. So the Rms block should be of a frequency 50 Hertz since the source is 50 Hertz. Apply OK. So let me flip it. So I want to flip this Rms block. I will flip it left to right. So now it is flipped left to right. Now I will connect this Rms block with the current source. And now I will have display in order to show the value of the current source. Again, I need to flip the display. So I will go right click, flip, and I will flip block, and then it will be flipped like this. Since it's the only current in the circuit, so I will type here I, ampere. So this will be the current in the circuit and measured in amperes. Okay, now I'm done with the current measurement. So now I want to see the voltage measurement. So I need to measure the voltage across the three elements. So let's start with the resistance. So as you see, I need to flip this block. I will flip it clockwise. So I will counterclockwise. So flip counterclockwise. And then I will connect the positive terminal to the positive terminal, the negative terminal to the negative terminal. Again, I need an Rms block. So I will copy this one and I will paste it somewhere here. So it will show me the value of this voltage, okay? So I will connect it like this, and I need as well a display. So I will copy the display and then I will paste it, and then I will connect the display to this Rms block, and then this will be the voltage across the resistor. So I will call it VR. So it will be VR, and VR, and VR is measured in voltages, in volts. VR is measured in volts. So this is this will be the voltage across this resistor. So I need to have the same block to do it across the inductor. So I will choose all these components holding the shift button, and I will select all these components holding the shift button. And then I will do right click, do copy, and anywhere in the system, in the model, I will do paste, and then I will use them by the arrows or the mouse to bring these blocks up here. So now I can connect them, connect the voltage source across the inductor. So the positive terminal to the positive terminal, and the negative terminal to the negative terminal, like this. So now everything is connected. I need to have the environment block, power GUI. So I'm typing power, here is power GUI, and I'm selecting it, and I should have it somewhere in the system. Okay. Now I need also to measure the voltage across the source. So again, I need to have all these blocks already copied. So I will do another paste, and I will use the mouse or the arrows in order to bring these blocks here closer to the source. Now I want to flip the voltage source. So I want to flip it in the counterclockwise direction, or rotate it, sorry. So I will rotate it in the counterclockwise direction. And now I want to flip it up, down. I want to flip it up, down. So I will flip it up, down. Now the plus is connected to the plus, and the minus is connected to the minus. Of course, you can do whatever you want in order to make it nicer. So it you can do whatever you want. Okay. And you can all the time click this square so you can maximize the use of the pitch. Okay, now I need to connect the power devices. So I need to connect the power across the resistor and across the inductor and one across the source. So for all elements. So first of all, I have this power device. Okay, let's double click on it. Let's make it a frequency of 50 because we have 50 hertz in this circuit, in this model. Let's remove all numbers, just keep one because one is the fundamental signal, the fundamental signal sine wave of a frequency of 50 hertz. So apply and okay. And now I want to connect the voltage value. So let me, in order to make it maybe much more clear, so let me take this voltage up, voltage measurement down here. So let me just try to make it a little bit nicer. Okay, now I will click this square once again, and I want to copy this voltage power measurement, sorry, once for the capacitor here, and another one for the source, another one for the source. Okay, this is for the source. Okay, now I see that I need to have the voltage of the source connected here. So here it is the voltage of the source, and I need the current in the circuit, and the current in the circuit is here. Here is the current in the circuit, okay? So this is the current in the circuit. Now this is the voltage across the resistor, and all voltages or currents should be taken before the RMS block. And we need to have the current in the circuit, and the current is the same current in the circuit. So it will be the same current, so you can drag it even from here if you wish. And again, here the voltage is the voltage across the inductor and before the RMS block, and the current is the current in the circuit, and I will take it from here. It's fine. So I can take the current from here, okay? Now I need to have some display blocks in order to be able to show the different values, right? To show the different values. Okay, so let me have one display here. Let me have, okay, all these displays. Let me bring one display. And I will connect this display here, and I will copy paste it. So copy, I will paste another one here, and let me make it just okay, and I will paste a third one here, and we need for the reactive power as well. So I'm copy paste the displays. Okay, so here are all the displays. You can also click this square button in order to make it nicer. So here we have them. So we can say that this is the power measurement of the source. And here is the power measurement of the resistor R. And here is the power measurement of the capacitor C. Sorry, the inductor L. So this is the inductor L. Okay. So this will be P in watts. So it will be P in watts. And this will be, let me say PL. PL in watts. This will be, this one will be QL in volt ampere reactives var. This will be PR, the average power in the resistor in watts. This will be QR, the reactive power in the resistor measured in bars. We expect that this value will be 0, but we need to measure it in order to make sure that we are doing fine. And this will be P of the source. So it will be PS, comma, in watts. And this will be Q of the source, QS, comma, in volt ampere reactive. So now I think we are fine. So let's make the stop time to be for one period, which is 0.02, 20 milliseconds, since 1/50 hertz will be 20 milliseconds. So let's see, let's run the circuit and see whether everything is fine. Okay, so we ran the circuit, and what we see that the voltage RMS value is 7.07, which is 10 divided by square root of 2, which is correct. We see the active power delivered by the source is the same active power consumed by the resistor, which is also correct because the inductor has no active power. It's almost 0. And we see that the reactive power delivered by the source is consumed by the reactive power by the inductor. It's equal to the reactive power of the inductor because the reactive power in the resistor is equal to 0. So I like to switch this numerical display to bank. Actually, bank is related to money, but it's fine here because it shows me only 2 digits after the decimal point. And this, let me change it to bank and then apply and OK. So as you see that we don't have any average power here. So again, let me run the circuit. Once again, we see that it is 0, it is 0. And this average power in the source is equal to the average power of the resistor, and the reactive power of the source is equal to the reactive power of the resistor, which means that everything is fine. And this is the current, the RMS value of the current in the circuit. As you see that this voltage and this voltage cannot in any form equal to this voltage because we cannot add them algebraically. You need to add them using or taking into account the phase angles between them. So you cannot check by the voltage having these numbers. Okay, so these are the average powers and the reactive powers for all components of the system. And of course, the apparent power for each one of them is equal to the average power square plus the reactive power square, and you take the square root of the result. So this will be, so the apparent power here, it will be 7.949 because the other one is 0, and the apparent power here will be 8.324, and because the other one is 0, and the apparent power is measured in volt ampere. Or you can multiply the RMS voltage, which is 4.88 for the resistor, by the RMS current, which is 1.6. And if you do this multiplication, you will get 7.949. And if you multiply this number, 5.114 by 1.628, you will get 8.324. And in order to find the apparent power for the source, you multiply the RMS value of the current, 1.628, by the RMS value of the voltage of the source, which is 0.071. So this is the voltage of the source. So let me change this R to S. Okay, and it is measured in volts. So let me see whether all names are correct. This one is incorrect. So it will be VL, the voltage across the inductor measured in volts. So let me see whether all names are correct. Okay, now they are correct. Now what we need to do is to find or to show the instantaneous power of the inductor in the scope. So we need to have a scope, or let's have a product block first. So we need to have a product block. So this is the product block, and in the product block we need to multiply the voltage of the across the inductor by the current through the inductor. And here is the current through the inductor, and the output will be the instantaneous power in this inductor. We need to show it in the scope. So here we have a scope, and the scope we need to have it 3 inputs. So you select the number of inputs to be 3. One input, sorry. So one input will be the current through the inductor. The other input will be the voltage across the inductor. And the third input will be the instantaneous power, which is the product of the current and the voltage. So now let's run the circuit once again, and let's see what we have on this scope. Okay, so it's a very nice picture as you see here. So let me bring the legend. So view legend, so we can understand what are these signals. So as you see, the first signal, which is the blue one, is the voltage. As you see here is the voltage across the inductor. And the voltage across the inductor was measured to be 5.114. This is the Rms value. If you multiply it by square root of 2, then it will be the maximum value. And as you see here is the maximum value, something around 7 something. This is the product of 5114 times the square root of 2. So if I do this multiplication using my calculator, so the current is equal to 5.114 times the square root of 2, then it will be 7.232. So this value is 7.232. We can double check this value. You go to tools, and then you go to measurements, and then you go to cursor measurements. And once you click that, we will have these guys. Let's say, let me enlarge the screen a little bit. So let me enlarge it a little bit so we can see what we have here. So as you see here, we have a cursor measurement. We have this line, number 1, and this dashed line, it has number 2 here behind the legend. Okay, so as you see, it is related to the yellow signal, and the yellow signal is the current. So I can change this signal from here. So I want to see the voltage, so it will be now the voltage. You see the dot, the blue dot is now here. So if I go and look for the maximum value, so this is the maximum value, I think. So it is 7.2, and this is what I got in the calculator. So I got in the calculator 7.23, and if I change it, so it's almost the same value that I got in the calculator. Here it is. As you see, this is the peak value, and this peak value is occurring at this time. Okay, so of course you can also switch to the other scale and see what values you need here. So what we need to see again. So let's have a look at this screen. So this is the voltage, and we double check that the values are correct and match. And here we have the current, and what we see that the current lags the voltage. How I can define that? So you see that the peak of the voltage occurs before the peak of the current. This means that the current lags the voltage. And as you see, when the current, the voltage is maximum, the current is passing through zero. When the current is maximum, the voltage is passing through zero. This means that they are shifted by 90 degrees. And this is actually what, this is actually the relationship or the phase angle between the voltage and the current. The phase angle is 90 degrees, and this is why we see that they are out of phase by 90 degrees. Okay. And the red signal here is the product, and the red signal is the instantaneous power, And as you see, this instantaneous power is of double frequency. So we see only one period for the voltage, we see only one period for the current, while for the power, instantaneous power, we see two periods. So this means that this signal is of a double frequency. So if the frequency of the voltage and the current is 50 hertz, so the frequency of the instantaneous power is 100 hertz. And we see that this sinusoid, the instantaneous power, is symmetrical to the x-axis. So the average of this sinusoid or double frequency instantaneous power is equal to 0 because it is symmetrical with respect to the x-axis. And this is why we see that the average power is equal to 0. So there is no average power in the inductor. And the reactive power, by definition, the reactive power is the peak of the instantaneous power. So, and as you see here is the reactive power 8.324, and here is the peak gives the same value. We can also try to trace this peak value. So I switched to the red line, and now I will hold this and move it. So it is 8.257, which is almost the same value. So I can move it to trace and to find the exact value, but of course it's not easy to control the mouse. But as you see, it's almost the same value, which is the peak. So this is one of the most important things that you need to know from this experiment, that the peak, the reactive power in the inductor or in the capacitor is the peak value, is the maximum value of the instantaneous power in this capacitor or inductor. Because in reactive elements, and here the example is for the inductor, in reactive elements, the inductor or the capacitor, the instantaneous power will be symmetrical to the x-axis, and its average is always equal to 0. So this is what we have here for the, and of course we should have a power balance. So the power delivered by the source should be equal to the sum of the powers consumed by the passive elements, and the reactive power delivered by the source should also match the reactive power consumed by the passive elements. Now, what we need to do is to do RC circuit. And what I want to do, I just want to change the type of this inductor. So I will double click on this inductor. I will choose it now to be a capacitor, and I will choose its value to be 0.001 farad. I will do apply, I will do OK. And now let's go for the, let's say, names of these displays. I want to change it to VC, and this will be the capacitor value. It is 0.001 farad, and this will be the power in the capacitor, and this will be the average power in the capacitor, which again should be 0. And this will be the reactive power in the capacitor. And before running the circuit, I want to bring your attention that for the inductor, the reactive power was 8.324. So it was a positive value. So this is, I want you to remember that the reactive power is a positive value. So now let's run the circuit with this capacitor. So what we see that the reactive power of the capacitor is negative. This is why we see that the capacitor seems to give the system reactive power, to supply the system with reactive power. And this is why we use capacitor banks to enhance the voltage profile in the distribution systems. So we install these capacitor banks in order to use the reactive power in these capacitor banks instead of dragging the reactive power from the system over the transmission lines. So what we see that the average power is the same. It doesn't change because we have the same resistor, the same voltage source. We see that the reactive power in the voltage source matches the reactive power in the capacitor. And if we look to the scope, we see the same values. We see the voltage, which is the blue line. We see the current, which is the yellow line. Now, if you noticed that the voltage, the current, which is the yellow line, leads the voltage because its peak occurs before the peak of the voltage. So the current in the capacitor leads the voltage across the capacitor. And we see that this is the double frequency instantaneous power, where its maximum equal to negative 83.1. We can trace it, try to trace it. So I think somewhere here. So it is this value. But of course, if you can move it very slowly, tune it. Now it is it will be closer to that value. It will match it for 100%. So this is the instantaneous power through the capacitor. In the capacitor, where we see again its average is equal to 0 since it's symmetrical to the x-axis, and its peak is equal to the reactive power of the capacitor. So in this video, as you see, we demonstrated the RL and RC circuit. We saw all types of powers. And of course, we know that to calculate the power factor, we need to divide P over S. And S, which is the apparent power, is equal to the square root of the real power square plus the reactive power square. So if you do the square root of the real power square plus the reactive power square, this will be the apparent power. If you divide P by the apparent power, it will be the power factor, So the power factor for the resistor will be 1. The power factor for the capacitor, pure capacitor circuit, or pure inductive circuit, it will be 0. It will be 0 because cosine 90 is 0.